Hello everybody. Sorry. We're gonna talk a little bit more about our number theory, and this time about integer representations. And this is something actually you know. For instance, what does it mean here? That is, we all know the decimal system. Now, I'm not referring to the actual what we call decimals, the digits behind after the period, but we are talking about the representation of, let's say, 2000. This, if we write 2440, what do we mean with that? We don't mean 2 plus 4 plus 4 plus 0, right? We mean these are the units. These are tens, this is 100, so units of course corresponds therefore just to 1, right? And this is the number of thousands. So 2 times 1000 plus 4 times 100 plus 4 times 10 plus 0 times 1. Okay? And this, of course, if you, even a nicer way to write this is 10 to the power 0, 10 to the power 1, 10 to the power 2, and 10 to the power 3. The reason that we start from 0 is that this is therefore it's the fourth digit, which is 10 to the power 3. Okay, that's a little bit, we know this, but we have to be careful with this. Okay, so we're using, that's why decimal, in the word decimal is the word for 10. Deca is the Latin for 10, but in many languages it's the same word. In English, 10 is also derived from that same root. It's not immediately apparent, but you have to. There's a field called linguistics where this is explained, that the word 10 in Spanish, for instance, it's much easier to see diez, and the C and Z are almost the same, right? In Spanish, you almost pronounce them the same, so you see it better there. Also in French, these, and so you, depending a bit on the language, you see better the thing. But it refers to 10. That is what it refers to. And so the base, this is, we call this, let me use the word that we call this decimal system, let's call it decimal expansion. Means we use base is 10. Now we can use any number bigger than 1, of course, otherwise it's kind of silly. Well, we could use 1, right? But then, yeah, that's just basically tallying, because the powers of 1 are all 1, so it's kind of not. But from base 2 is, of course, binary, refers to base 2. And also that's something that I'm sure all of you are kind of familiar with. So for instance, 1 0 1 1 0 0 1. What does this mean? If this is a binary number, then this means we now take the powers of 2. So, and we start with the 0th power, the 1st power, the 2nd power, the 3rd power, the 4th power, the 5th power, 4, 5, and this is the 6th power. Okay, 1, 2, 3, 4, 5, 6, 7 digits. Okay, we've seen the number of digits is 1 less than the power. It's one more than the power. Now, of course, when there is 0, we don't count it. So what we get is the ones that count are this one, this one, this one, and this one. So this, of course, is just 1. This is 8. This is 16, and this is 64. So the powers of 2 are something you kind of need to know in order to calculate this very quickly. Of course, the powers of 10 very, very simple for us, right? Because we are working in base 10. The powers of 2. So we would have to add up all these numbers to get what is this binary number represents in our decimal system. So that would be 70, 80, 89. I hope I didn't make a mistake here. Okay? So to make a distinction, of course, if I just write, let me get rid of my, well, okay, let me just circle this. So this number here, I told you it's binary, but it could also have been a decimal number, and then of course it's completely different. Then it would be 1,011,001, right? So we need to know what, if we use different bases, we should denote the base. And we will do this only basically in this section, but just to, so we would write the base at the bottom here. So what I was really calculating was this, and so what we say that this is equal to that. 89 in our usual, so if I don't write a base in this section, I mean the usual base, the decimal base, but I'll try to make, at least when I formulate the problem and during the calculations, we're gonna not always keep writing this, but okay, what other bases are there? Well, any number. So how does that work then? Well, so we have a base, but there's also something called the digits. What are the digits here? 0, 1, 2, 3, all the way, well, let me write them. It's not that many, right? 8 and 9, not 10. Notice that these digits is exactly what we called Z10. Z10 were the remainders by division of 10, and that is exactly these digits. So what are the digits here? In base 2, the digits are only 0 and 1, which is just Z2. Okay, so the digits, so if we have expansion in base B, where B could be any number, at least 2, so I say B at least 2, as I said, it's stupid to do this for B, because one can think about it for a sec why, so what does that mean? We're gonna write this, we will have our digits will come from the set ZB, which is the set of all remainders by division mod B, 0, 1, 2, all the way up to B? No, B minus 1, right? One less. So these are B possible digits that will be used in this representation, and this will be, and then we will write this so as a d b to the power d plus a d minus 1 b to the power d minus 1 plus a1 b plus a0 b, and then a d minus 1 up to a0 are our digits in base B. So these are the, and so the thing is that all these A's must belong to ZB. Okay, that is how such a representation looks like. Now there is a major problem here for us notationally, because these AD minus 1 and so for instance, let's say let me look at a case which we use a lot and where this problem is apparent. The hexadecimal system. Okay, so again, deca means 10. What is hexa? That's Greek for 6, which is the same as 6 says. The H is perhaps throwing you off a little bit, but okay, that is just the way Greek works. But it is the same root, so this is 6. So this 60? No, 16. Okay, so this means 16. So this is, I'm just analyzing the word, right? It's just a word, a name, but it means that the base B is 16. So what are the digits? So the digits should come from our collection 0, 1, 2, 3, all the way up to 15. That's the remainders by division mod 16. However, look at the problem now. Suppose I want to encode the following number: 11 times 16 plus 5. Right? So okay, yeah, sorry. I should perhaps, before I do the hexadecimal system, let me do a system where we don't have a problem, because perhaps otherwise you don't understand why there's even a problem. Okay, let me move this a little bit, and let me do first. Let's do what is called ternary. Can you guess what base it would be? Ternary 3, okay, base is 3, so our digits will be from Z3, which is 0, 1, and 2. So for instance, if I write 2, 1, 2, 0, well, let me write the 0 somewhere else, otherwise it looks like the 0 is on the back. This in ternary, what does this now mean? Okay, this means 2 times 3 to the power 0, plus 0 times, I'm not writing that, plus 1 times 3 to the power 3, so yeah, I should have written it here, 3 to 1, 3 to the power 2, otherwise I lose track. Okay, so again, the only ones that count are this, this, and this, but we have to be careful now. Now we have to do twice, this is 1, right? Twice, so this is 2, this is 1 times 3 squared, that is 9, and this is twice 3 to the 33 to the 33 is 27, so this represents twice 27, that is 54. Okay, and then we add all these numbers, and that is what this number means then in decimal. So 63, 65. So this is 65 in decimal. I want to emphasize the right term, but I've said if I don't say, then I mean just our decimal system. Okay, so no problem. This is clearly no problem. But what about this number here? So this number, let's work out what it is, right? It would be 11 times 16, that's 1676 plus 5, so that is 181. So that's the decimal, okay? In decimal, everything was decimal, but just to emphasize, my answer is in decimal, written in decimal. So how would I write this in hexadecimal? Now, if we would take 11 and 5 as our digits, then we would write 11, 5 in hexadecimal. But this is a problem, because what do I mean here with this 1, 1? Do I mean 11, so that in other words, this is one coefficient, this is another, or do I mean 1, 1, 5? Strictly speaking, so this is what I would think. So the question is this the correct representation of that number? No, because what does this mean in hexadecimal? 5 would be the coefficient of 16 to the 0. This is a number, that is the digit, that is a coefficient of 16 to the power 1, and this would be 16 to the power 2. Okay, 16 to the power 2 is 256, this is 16, and this is 1, so this would correspond to, well, we have to do this times 5, right? So this would correspond to 5, the other 2 plus 1, so that would be 61 to 77. Did I do that correct? No, I didn't do it correct, right? No, I did correct, okay. That's not the number that I wanted, 181, so this is decimal again. What's the problem is that when we write down the Z, so this is Z16, right? I forgot to write this, so Z16. The elements in Z16, we write them as ordinary numbers. Often, what one does is to make difference and say these are not really different, these are not your regular numbers. One puts a bar on top of it. And then we have a bit better situation. If I put 11 bar, now I know if I write it, so let me write it there. So this is a better notation, 11 bar, 5 bar, because this is now a single coefficient, and this is a single digit, therefore a coefficient, a digit, right? And this is a single digit. This is the digit from 16 to the power 0, this is the digit from 16 to the power 1, and that gives me exactly the number that I wanted. So this is how I should write this. So this is not correct. Now, 11 bar is something that perhaps sounds a bit weird, and to write 5 bar is even sillier because there is no need to write that. Why? So I emphasize, why do I need to put a bar on top of 11? Because I need to make sure that 11 is considered as a single digit, and so if I would instead want to represent this number here with, this number with the bar notation, what would be the difference? Well, it would be 1 bar, 5 bar. So you see the bars are split over each of the ones, making them each a separate digit. Now, that's not how we solve it in hexadecimal, because as I said, these bars are annoying. So we have 10 bar, 11 bar, 12 bar, 13 bar, and 14 bar. Well, we use different notations for that. We call it A, B, C, D, E, and F. And therefore hexadecimal, so in hexadecimal we would actually write this 11, so 11 corresponds to 11 bar, if you want, corresponds to B, so this would be B5 in hexadecimal, and we don't write a bar on the 5 now anymore. And that's what hexadecimals, I mean, I'm sure many of you have seen hexadecimal numbers. They have these letters in there, not all letters, only A up to F. They act as the digits that would correspond in decimal by where we need in decimal two numbers to denote them because they're bigger than 10, 10, 11, 12, 13, 14, 15. Okay? So, strictly speaking, therefore, if you design a system in a certain base, you need digits for each of the, you need a symbol for each of the, for each of the elements, each of the digits, each of the elements in ZB. So this ZB here, we need names for the elements in ZB. One solution is by putting a bar on it, and that is a solution that mathematicians do, but that is not practical. And hexadecimal is used a lot in computer science, and for practicality purposes, one replaces these bars by A, 10 bar, 11 bar, and so on, by A, B, C, D, and so on. Okay? So that's the first thing that we need to talk about. Now, the second thing is then how to convert. And that is, of course, important to do conversion from one into the other. We need to do that sometimes, right? So let's start with that. And let's do a general thing. So find the expansion in base 7 of the number, I'm going to make up something, 1500, this one. So here I mean the digit, this guy. So here's the algorithm. So what we do is, if you can do everything as an algorithm. So step 1, what we will do is we will calculate, and this is important that you have to keep this in mind, we will calculate the digits from right to left, rather than from left to right. There is a way of calculating from left to right, but it involves a little bit more guessing in some sense. It's sometimes more practical, but I'm going to describe the one that goes from left to right. So in other words, the first digit I will find will be the digit will come all the way at the end. That's something we have to keep in mind when you give your answer. Otherwise you lose a point there on the quiz or whatever, whenever we use this. Okay, so how does it work? So we calculate our number, so n is the number, right? So it is really an algorithm, but I'm going to not write the pseudocode here. What we do is, the first step is n mod b. We will calculate n mod b. What I mean is, I mean here really the mod function, right? N mod b. Okay, so, n mod b. So in this case, what we do is 153 to mod 7 was my base. Now, remember how did we calculate this? This is 2 steps. Step A, let's go. We calculate 53 div 7, and that is what we do is we divide this by 7 and take the floor. So 1532 divided by 7 is 218 point. That is 218.8. So the floor of that would be 218. And then step B is we take our original number and subtract from that 218 times 7. I repeat, so where does everything come from? The 218, that's the diff that we just calculated, and the 7, of course, is in this case the base. It's this 7 is this 7. Okay. Okay, so we calculate this. 218 times 7, and then I subtract from that. That is 1532 minus 1526. That is 6. Okay, and this is our first digit. Okay. Well, let's write down what we have in. So I'm saying we calculate this, but what this gives is the division algorithm. So the division algorithm now I can now write down the division algorithm tells us that this is 1532 is 218 times 7 plus 6. Okay, this is really basically what this equation says, right? But it's good to write this down because the next step we do is, so it is a loop. We take this new 218 and do exactly the same thing. So we're going to divide 218 by 7, and calculate the remainder. So here, of course, this will be 218 diff 7, and this number that we're going to plug in is 218 mod 7. Okay, so again, let's do this. 218 divided by 7, that is 31.1. So this is So this is 31.1, so it is 31. So if I multiply this, it is 200. So this number here is 217, right? 210 plus 7, 217. So we need an extra 1. That's we see it right away here, right? So 1. Okay. So we do this now with 31. So 31 is, if we divide by 7 again, so this we can do by hand, so to speak, right? It's 4 times 7, 28 plus 3, and we do one more time, 4. Can we do this? No, 4 is already a remainder. So this is already instead 7. These are the digits, right? And so we're done. Notice that each of these numbers are also digits. Now, what did I say? I said the digit that we calculate, and this is 4 is the last one. If you want, you can also think of it this way. 4 is 0 times 7 plus 4. And here, if you have it there really as a remainder, because if you divide 4 by 7, the quotient or the div of that is 0, and so the remainder is 4. And so this 6, 1, 3, 4 are now the digits, but I emphasize in this order. From this is the lowest to the highest digit. Okay, so that is. So in other words, I should start from 4, 4, 3, 1, 6. Perhaps my arrow was a bit misleading. I don't know what I meant to write here with my arrow. So I mean, this is perhaps more this way, right? So these are the digits of 4316 mod 7. Okay. Let's do one more. Let's do 177130 in our regular bit in hexadecimal. Okay, because hexadecimal has this added problem that we have some of the remainders are numbers more than decimal numbers with 2 digits, so we have to call them not 11 but B, etc. So let's work that out here. So the same thing. So B is 16, and so we do out the division algorithm. We start with our number 177130. How many times can we divide by 16, and what is the remainder? So here what will come is 177113 div 16. Here we put 177130 mod 16. Sorry, I'm going to put it in here. So this is a div and this is mod. Sorry, it gets a little bit. So we calculate this. It turns out that this number is 11070. Dot a little bit, but we always floor it, right? And then the remainder is 10. Okay, so this will be our last digit, but remember 10 is not it should be 10 bar, but 10 will become A, but we'll deal with that later. We continue our operation. This becomes the new number that to work with. We have to write it as a multiple of 16 plus, so divide by 16 and we get the remainder. I'm going to do this a little bit quicker, so I'm going to calculate these things very quickly here. I hope now how you know how to do this, right? So this is 691 if you do this. Repeat, what is this? This is 11070 divided by 16 and then you floor it. Okay? And that number turns out to be this, if you calculate this, is 11056, this product. So what is left is 14. Okay, so that's the division algorithm, and we keep doing this. This is a process that we will do several times things like this, so you have to get used to it a little bit. So we keep doing this 691. sorry, 691, we're going to divide it by 16 and then take the floor. That will be this coefficient here. This turns out to be 43. Please verify my calculations, but I'm actually copying it from the book here, where they have to calculate it for us. And then if you multiply 16 times 43, you see you get 3 less, so 3 is the remainder. Okay, so this will be our next digit. But let's focus first, let's not talk about the digits yet, let's talk about the consecutive divisions that we have to do. We take 43, and we divide it by 16 again. This becomes easy, right? We can put 16 there twice, 32, and then what is left is 11, right? Okay, and then finally we take this 2, sorry, not circle it, let me box it. 16 is always the same number, right? But these numbers change. We do one more time, that's 0 times 16. Of course, it's silly to do this, but just to show you that how 2 appears as a remainder. So these are now the digits in hexadecimal, but we know that this digit actually is written B. 14, I don't know this by hand, so I'm cheating. 14 is E. Yeah, I could have. If I think about it, I can figure it out, I guess. And 10 is A. So this number in heptadecimal, make up the word, but I don't know, probably it's correct, but I don't know, is, well, we have to list these things from the bottom one first. 2, B, 3, E, A. And I repeat, what am I doing here? These are these guys, right? These guys here, that's these guys, and I'm doing it in this direction, if I from left to right. And that it's the, 16, excellent. Oh, okay. Why did I say hexadecimal? I'm thinking of the previous one. It's 7. We did this with base 7. That was the previous one, right? Yeah. Okay. Sorry. Okay. So now some conversions. Of course, some of conversions are easier. Let me do that quickly. So let's suppose I know that this number now, and I want to write it in binary. Well, because binary B is 2, well, what will be B? But what are the numbers that B equals 2 with base 2? Any number in set 16, so any of the remainders, so in other words, 1, 2, 0, 1, 2, 3, all the way up to F, each of these in binary require exactly 4 binary digits, right? Because any such number, so for instance 2 in binary will be 1, 0. B in binary, what is that? B in binary is, where is B? B was 11. So let's think about it. This is 8 plus, so B is 11. That's what it stands for. And in binary, this is 8 plus 2 plus 1. Remember, we write it as powers of, so sorry, this is binary, it could get confusing otherwise. So in binary, this would be 1, 0, 1, 1. Do you see why there's a 0 there? Because there's no power of 4, right? Be careful. Just because it's not there, that means that there has to be a 0 there, right? Be very careful with that. Okay, so in binary, this is that. This is the binary for 2. What's the binary for 3? Well, 1, 1, right? What's the binary for E? Well, E is 14. Yeah, E is 14, which in binary is, let's see, 8 plus 4 plus 2, which in binary therefore is 1, 1, 1, 0. And finally we have also A, right? A, yeah, A, that's 10. That is 8 plus 2, which in binary, the 8 is that digit will be a 1. The 4 digit will, that's the power, that's the coefficient of 4, right? This next one is coefficient of 2, this is coefficient of 1 in the expansion. So this is that. So now, that means that we can replace these by that, but we don't want to write the 2's there, right? So now what in binary now, but that's why we have to be careful. Notice, as I said, each of these require 4 binary digits, at most, perhaps, right? Because these two need less digit, but we want to always write it as 4, and that's important. So every digit has to now be represented, every hexadecimal digit has to be represented in binary by 4 binary digits. How do you do that? Well, so you pad it with zeros in the front, right? Remember, even in decimal number, 100, you can write 0, 100, and it still means 100. We sometimes do that, but just to make everything like aligned, so to speak, right? So I'm sorry, this was now meant as decimal here, but okay. But the same is true for binary. So I'll pad it here with, and now I can replace, so 2 becomes 0, 0, 1, 0. Let's group it a little bit by in fours. B becomes 0, 1, 1, 1. 3 becomes 0, 0, 1, 1. I'm just looking here, I'm taking this order and I'm then replacing it by the calculations that I did here, right? Just if you follow. Then 1, 1, 1, 0, and then 1, 0, 1, 0. So this is the binary grouped a bit in fours. Note that this is something we also do sometimes with decimal, right? We use commas to write a million. We could write a million this way sometimes, or we can, it's really the same. But you see, the more I structure a little bit, the more legible it becomes. So it's often, the practice is to write it this way in groups of 4, exactly because it allows a very easy transformation from hexadecimal to binary, and other way around. Suppose this is a binary number, without calculating what number this is. Let's find what is the hexadecimal of this. Well, what you do is now you group, or let me do, okay, sorry, I'm gonna make the number a little bit different. Let me make it this number. You take groups of 4. Remember, because every group of 4 binaries, a binary number with 4 digits corresponds to the numbers 0 all the way up to 15, which is exactly the digits for the hexadecimal. Now, the last one, 4, 4, but then I have 2 left. Again, I padded with 0. And now I just calculate what is this. This is supposed to be the number 2 plus 8, 10, which is just A. This is the number 11, which is just B. Okay, that's a bit illegible. You can see what I'm doing, right? And this number, which is 2, and that's just 2. So this would be 2BA in hexadecimal. Okay. The textbook likes to also work with octal. It's not so common anymore. Binary and hexadecimal are the 2 most frequently used systems in computer science, and of course decimal in our regular mathematics. Okay. In the book they also describe how to add and multiply. But the idea is, I don't want to do this too much because I think I might even have done. Let me do an example of how you multiply 2 binary numbers. Let's multiply these binary numbers. You do exactly as you would do in division, in multiplication, long multiplication in decimal numbers. But you just have to think that the carryover, when does the carryover happen? Okay, let me show you what I mean by that. Let's first do the addition, perhaps. So yeah, so sorry, first addition. Sorry, I wrote it down, but I don't know why I wrote it one more time. Okay, so addition. Sorry, I don't know what's going on here. What am I doing? Come on. Addition. Okay, we add digit by digit. 1 plus 0, 1. 0 plus 1, 1. 1 plus 1, 2. No, because we only can have zeros and 1. So this is the same as when we would in decimal would add 9 and 3, we would have 2 carry over 1. So we have a carryover here, we get 1 plus 1, that becomes a 0 carry over 1. Right? So in other words, visually, let me show you this, what I mean visually here. If we okay, let me do this here. Suppose I'm adding 9 and 3, adding. That is 12. But what we do is we call 1 the carryover and we put it on top here because there could be other numbers. Let's say we have this also to do. So we don't put a 1 there, we put a 1 there and then add it to the rest. Then we do 1 plus 2 plus 1 and we get 4. Okay, you see how that happened? And so this is exactly what we happen here too. 1 plus 1 is 0 and 1. And now, if there's a, just let me do this. Suppose we have to do this one now, sorry. Let's do addition of these two numbers. Okay. Okay, so this one we had to carry over 1, we put a 1 here. I'll one more time, right? 1 plus 1 is 2, which in binary is 1, 0. So we put the 0 here, but we put the second digit on top. And now we add all these digits, that is 3. But 3 is not binary, 3 is 1, 1. So we do exactly the same. We put the first digit, 1, 1, right? 1 there, and the other one goes up. And then we add to whatever it is. There's nothing left anymore, so we just bring it down, 1. So that is how how you add. So in other words, 1, 1, 1, 0 plus 1, 1, 1, 0 is 1, 1, 0, 1, 1. Notice that I'm doing this calculation without converting them. Of course, I could convert each number, add them up, and then convert it back into binary, but there's no need for. Okay, so this is how it works. I will do one example in ternary. Suppose I have to add okay, let's do this. So I have to add these. Now, when I'm doing it, I'm gonna not write the ternary anymore. Okay, what I mean to say is, what is this, right? I want to work this out in ternary without actually converting, because converting is time consuming a little bit, not very much, but okay. Well, let's do this. Addition, 1 plus 1 is 2. That is a valid thing, so there's no carryover, okay? So then 2 plus 0 is 2. Again, nothing to do. But here the first problem comes here, 4. So we get 4. That 4 is not a legitimate binary ternary number. 4 is actually 3 plus 1, so it's actually in binary 1, 1. Okay, so I'm replacing this 4, let me do it this way, by that digit 1, and I put the other digit up there. Okay, sorry, let me make, okay. Okay, so I'm going to replace now everything. So I said, okay, this has to now be 1. And then we have to add these two. Allow me to make this in a 2 as well. Okay, otherwise nothing too much happens. And I put here an extra 1 here. Let's put it this way. Okay, that they don't even have the same length here. Otherwise you would think that is necessary. So okay, we are this far. Now what we do is 1, that carryover, plus 2, that is 4, plus 1 is 5. What is that in decimal? So 5 in ternary, in ternary is 1, 2 in ternary, right? Because it's 1 times 2 plus 2. So we get a 2 here and a carryover 1 there. Notice that the carryover in this case can never be more than 1, right? And then we finally add 1 on 1, and then plus there's this. If there is nothing, then this means it's 0, right? So we get 2. So this is the ternary solution of my addition, without converting the numbers. Multiplication is the same, except that I'm going to do very quickly one multiplication here. So we would do exactly the same. We take, as with regular multiplication, we take this digit and multiply each of these digits with 1. So we get 1, 0, 1. And now we take the second digit, do the same thing, but of course we have to shift, because this is the second digit. So we do the calculation again, but now everything shifts 1 to the left. And then we add everything up. So 1, 1, 1, 1. That's the binary. Let's do it in ternary. So suppose I have to multiply these two numbers. Okay, so the 1 times 2 is 2. 1 times 2 is 2. 1 times 1 is 1. That is taking care of this digit. Now this digit, but we have to start at this position now. And then this digit and that, that and that, that and that. So that would be 2, 2, 1. But there's one more digit, this digit. Now we have to do 2 times 2. 2 times 2 is 4. Okay, now be careful, 4 is not a correct digit. In ternary, that is actually 4 is 1, 1, right? So there's a 1 here and extra 1 comes there. Okay, 2 times 4, that is again 4, but we get a carryover, so a 1, 1 again. And then finally 2, that's 2. So now we add everything up, but we have now these extra carryovers that we have, right? So, sorry, why did I write them this way? Sorry, I shouldn't have written it as carryover yet there. I was a bit too, I just should have written the 1 here, okay? So, sorry. No, it was correct, Okay, so now we have 2, 4, okay, that is 1 carryover 1, then 1 plus 1 plus 2 plus 1, that is 5, that is actually 2 carryover 1, and 1 plus 1 plus 1 is 4 carryover 1, I have a 1, 1 plus 1 plus 2 is 4 carryover 1, and this is the number in ternary. Okay, now I'm not going to deal too much with this. This is not really what we are interested in, but this is very important. Modular exponentiation. So remember that we have our ZB, and we can add, and we can subtract, and we can multiply. We will talk about division in the next lecture, but we can multiply here. Let me write it like that. Okay? And how do you multiply? You take two numbers, but then you take it. You have to take them mod whatever your modulus is. Okay? So that's how that works. In particular, now, since you can multiply, therefore, you also have the notion of exponent. Okay? So, if instead of b, let me take a different, let me call it n here, because that's what we're going to do in this equal n. So, suppose, so we can a times b, we can calculate that. So, for instance, let me do an example here. So, n is, let's take n 13, and then 5 times 8 mod 13. So one way of denoting that is that we work in Z13 is to write the multiplication here, right? And the meaning of that was you take 5 times h, which is 40, and then you mod, we take the mod 3, because mod 13. So 40 mod 13, of course, that is 40 is 39 plus 1, so 40 is 3 times 30 plus 1, so this is the remainder, so this is 1. Okay, a notation that I didn't introduce, but I hope you saw it in reading textbook and also the exercises. Instead of writing it this way, we sometimes just write things like this. So what has changed? It's very subtle. Instead of taking, this is a function with these two inputs, this, and this is regular equality, this is now an equality. It says that this number is equal to this number, and mod 13 means that these two numbers, when you subtract them, they're divisible by 13. Now this, of course, is stupid because it's the same number, but it's the second one that I want to say. So because the difference between 40 and 1, the difference between 40 and 1 is this multiple of 13. If the difference of these two numbers is the same, is a multiple of 13, then we say they are equivalent mod 13. So this mod 13 is a function, this mod 13 is an equality modulo 13. It's a subtle thing, but it is something that it kind of is immediate. It's the same notation read in a different way, and that's why we use a difference between boldface and lightface. But it is really not much of a difference. Okay, so we have a times b, but then we can also talk about in particular a square, a times a, and a cube would be a times a times a, and so on. So we can talk about a to the power k. Okay, this would be a times a all the way a, and how many times? Well, k times we multiply. That's what an exponential does, right? Okay, so suppose I want to calculate this here. I'm going to do it on an example and explaining how it works. Let me think. I want to do this a little bit. I don't want to do too difficult yet. Let's do 7 to the power 6 mod 19. Okay, I want to calculate this. Okay, again, see, I'm going to be sometimes sloppy here. This is really what I want to calculate. So what this should give me is a number between what and what? Between 0 and 18, right? Because 19 has, that are the digits for 19. So remind you that one more time, that Z19 is 0, 1, 2, all the way up to 18. Perhaps with the power over, if we, is there a confusion, but in this case, we don't worry about that. Now, granted, 7 to the power 6 is not a huge number, so I'm going to do an example later where the number is much bigger, but it is still a rather big number. Let me just do it on my calculator, see whether 7 to the power 6 is 117,649. It's not enormous, so allow me to do, I'm going to make it worse a little, because otherwise you might say, oh, this is stupid. Okay, but this is perhaps more telling. 7 to the power 22. What is 7 to the power 22? If I just would calculate it with my calculator. My calculator says 3.9. No, that cannot be. Oh, it says, it gives me scientific notation. So my calculator, the calculator, I'm not going to show you, you can try it on your own calculator. Each calculator might give it, this says it's 3 times 9 E18. What does that mean? Exponential notation. Remember, this means actually this 3.9 times 10 to the power 18. 10 to the power 18 is a huge number, a million times a million. Okay? A billion times a billion. It's a huge number already. Many zeros. 18 zeros. So it's 3.9 with 18 zeros. Is that correct? Well, no, of course. This is now an approximation. But with a number this big, remember, what I'm looking for is the rest. When I divide this number by 19, what's the remainder? But I don't know all the digits to do this. When you divide, think just about if you do what is mod 10. What is this? Because this is decimal, it's the last digit. It's just 5. So when you calculate when you calculate these remainders, what is important is not so much the leading things, it's the trailing, the last one digit. But this is exactly the opposite of what an approximation is. An approximation doesn't worry about the small digit here. There are 18 other digits here that are not correctly mentioned. They're all set to be 0, which is not true. So, and this is the order of magnitude. What we need to know is the last digit. Okay, so that's why the calculator cannot calculate this anymore. Now we'll see that this is an important tool to do, and this is exactly where we're going to use in cryptography. That we're going to use these numbers. So how do you do this? Okay, so I'm going to do it on this particular example, and then you can follow in the textbook and see how you do it in general. There is an algorithm in the textbook, but I'm going to do it take it a little bit more apart because it's easier to say. So step 1, and that is perhaps a bit surprising. So you take the exponent, in this case that's 22. So be careful to use the exponent in base 2, in binary. I'm going to write the exponent in binary. So 22 in binary, that is 16 plus 4 plus 2, right? So that tells me then 16, well, you have to be a bit careful. That is 2 to the 4, this is 2 to the 2, and this is 2 to the 1. So we're going to have 1, then a 0 for the 8s. A 0 for the 8s, then a 1 for the 4, then 1 for the power 1, and a 0. Okay? So that's the binary description. That's step 1. Now, we're not going to use it immediately. That's step 2. You take B, which is our number 7, that we're going to take the powers of, and so we do two things with it. Square plus take mod 19 of it. Okay, so what do I mean? I take, so 7, so here is 7, okay? 7 to the power 1, that is of course just 7. Now we take 7 squared, which is 49, but I'm going to take the mod 19 of it. So mod 19, now 49, just to do the, so 49, so what is, yeah, let me not write it that way. Let's do the calculation here. 49 is 2 times 19, which is 38, plus 11. Okay, so I find that this is 11. Okay, and now this is where it gets interesting. I'm going to calculate, so let me write this, this is the calculation, but we write this with our notation that I said is kind of the same, it's just writing it a little bit differently. So I'm going to write it here. So 7 is equivalent to 7 mod 19. Then the next thing I calculate is that 7 squared is equivalent to 11 mod 19. This is how you pronounce this. You say equivalent. And I remind you, this means two numbers. A is equivalent with B mod n means that they have the same remainder if you divide by n, and another way of saying that is if you subtract them, then they are divisible by n. Let's write it that way. So this means this, which also means, it also means that A mod n is B mod n. Sorry, it's a little bit squeezed in here, but what I'm trying to say is that if you calculate A mod n, you take the remainder of A modulo n, you take the remainder of B modulo n, then they are the same. That's what this means. Okay, but instead of writing this mod n twice, we write it once in the back, and instead of equal, we write equivalent. And it also means, because if you subtract these two numbers, well, they have the same remainder, the remainders cancel, and therefore this is a multiple of n. Okay, I didn't explain. I should have explained it a bit better in the previous previous session, but it explained it in the textbook. I hope you saw that. So okay, now, and this is the key point. What I'm doing, I take this. I'm going to take 7 to the 4th. I'm going to calculate the square of the previous one. So remember, square. So this is where I square, and then take mod 19. That's this part. Okay, or rather here that I did this. Now again, square, so here I'm squaring the previous one, 7 squared, squared is 7 to the 4th, right? But 7 is the same as 11, so it's 11 squared. And now I take do this up. So let me color them. Squaring is red and taking mod 19 is green. Okay, so here is the squaring. Sorry. This is where I square, and this is where I calculate the mod 19. Okay, then I do square again. Sorry. So I square again. Notice that there are two different numbers I'm squaring. The left one I square is just exponents, right? The square, 7 squared is 7 to the 4th. And then the next one will be 7 to the 8th, right? Okay. But then I also look at the result that I have and square that as well. That's so far just the square part, but now I take mod 19. So I'm going to, what is that? This is 121, and that I'm going to take mod 19. So here is, if you want, the other operation, the second part of my strategy. And what is that? 121 divided, let's calculate this. 1 to 1 divided by 19 is 6.3. So 1 to 1 divided by 19, that is 6. So I know that 121 is 6 times 19. 19 times 6, which is 114. Plus, and now I see that the remainder is 7. Okay, so this is 7. Of course, these numbers here that I get at the very end all have to be smaller than 19, right? Okay, I keep doing this. Now you ask how much? Well, until the 16th power. That's the highest power that we will see how we use the decimals, but we need to know this already. How far do we go? So we're gonna take, we are not there yet. So I'm gonna do one more time the squaring. So I'm now gonna take, here. So I'm gonna, that's not. Okay, so square this. 7 to the 4th squared is 7 to the power 8. Okay? But that is also this 7, this is the same 7. Yeah, sometimes I have this, that's a bit bad coincidence that against it 7. I didn't want to have this. Yeah, there's nothing I can do about it. It's okay. It's this 7. It's the news. It's this. I wish it would have been a different number, because then you would not think, oh my God, why is this 7 again? So whatever this digit is, I'll do another example later where you see it's not happening. I'm going to square this. So I remind you, this is perhaps, I'm sorry for this, that these numbers happen to be the same, but this 7 is this 7. Okay? This 7 to the 8. This 7 to the 4th, I square it and becomes 7 to the 8. Then I take this 7 and square it becomes 7 squared. Okay? That is 49, and I now take the mod 19 of that. So that's, again, the other operation that I do, right? And what is that? Well, we actually calculate that. We know that this is going to be 11. So actually, it makes our calculations easier, because we're going to repeat everything again. So next step is square this as well as this. Okay, because they're going to equal. Yeah, sorry. Right, let me keep track. I didn't keep track here, but I should keep track here of this. So the previous, this tells that 7 to the 4th is equivalent to 7 mod 19. What I just calculated is 7 to the 8 is equivalent to 11 mod 19. And so now I square this again. What happens if I square 7 to 8? I get 7 to the power 16. What do I get if I square 11? So 11 squared, that is 121, and I calculate this again, mod 19. And that is, we have already calculated, it happens to be, again, 7. So what we find is that 7 to the 16th is equivalent to 7 mod 19. I reiterate, the fact that we get the same numbers here is just coincidence. Normally this is going to be all different numbers here. All smaller than 19, because they're all remainders. So we get this, okay? So I'll do another example that hopefully is clear how it works. So this is 7 squaring, this is this number squared. So we have squared this number now. So I don't know how to indicate it, that this comes from there. All right, now you stop. Why? Because 16 was the highest power of 2 that I needed, okay? So here is the beautiful thing that I'm going to write. So remember, this is what I wanted, 7 to the 22. Now, 22 is in binary 16 plus 4 plus 2. 16 plus 4 plus 2. Okay? I'm writing 22 in binary, but I'm not writing it in actual binary. I just split it up in powers of 2. Now, this is the beauty of exponentiation. Do you agree with me that this is the same? Right? Because if you multiply the same base, you add exponents, right? So this is that. Now notice that we have calculated each of these guys that appear here. Some of them we calculated, but we don't need them. So shouldn't we have calculated? Yes, we needed to calculate the next one. So we need to go from all this way, otherwise we're not getting, we need to calculate each of these by successively squaring. But not all of them we're going to use. We only use the ones that are now coming in these 3 coming from the exponential. So we now going to calculate this mod 19. So now this is, I write this as, the first 3 were equal. So everything was equal. We're going to say mod 19 because now we are mod 19. 7 to the 16 is actually 7. 7 to the 4th is actually also 7. And 7 squared is actually 11. mod 19. And now I can calculate this. Also, you can multiply it all out at once and then take mod 19, but very often what one does is one combines two. So this is 49, so we have 49 mod 19, but we know already what 49 mod 19 is. We know that this is 11, right? So we know that 49 mod 19 is 11. Another way of saying that is that 49 is equivalent to 11 mod 19. Well, I have it here. Well, I didn't spell it out. So this number, that's 49, is the same as 11. So this is 11 times 11 mod 19. And 11 times 11, 11 squared, that we also calculated here. For instance, here's the 11 squared, that is 7 again. I'm sorry that we have this. It might seem that I'm going to do another one. I wanted to not do it, but I'm worried that you think that these numbers is 7 and 19, you might get a bit confused. So let me take the one from the book. It is quite a little bit of calculation. So let's calculate 3 to the 644 mod 3 to the 6 to the 4 5, which again the reason that is one more than the other is not really important here, but that's what we do. So the first thing we have to do is write 644 in binary. Okay, now that might be not so. I told you there are two ways of doing this, and that is by successively dividing by 2 and finding the remainders. Okay, so in binary this number is, I'm not going to show, I showed you how to do it, so I'm going to just tell you 1, 2, 3, 4, 1, 2, 3, 4 zeros, 1, a 0 and a 0 and a 2. That's the binary for 644. I'm trusting the book, so you should trust me trusting the book. Okay. Another way of doing this is also the following. You can say, okay, what is the highest power that goes in 644? Now, we need to know the powers of 2. In binary, it works in all decimal systems, but especially very well in binary, so that's why I'm only going to explain it in binary here. So these are the powers of 2 up to 10. This is 2 to the 10, 1k, that's what it says, and goes on. And these are numbers that are used so frequently that you better memorize this. You see, the highest power that we have is 512. So we can write this as 512, and what is remaining? 132. Okay? What's the next one? How many times can we put 256 in there? No. Can I put 1 and 2? Yes. So I can write this as 512 plus 128, and then 4 is left. And that is already a power of 4. Right? So you see the powers of that, the powers that occur are 512, 128, and 4. So I explain again, how did I get there? If I went a bit fast. Look for the highest power of 2 that is smaller than this number. That was 512. Subtract it, and you get 132. And keep doing this now. 132, the smallest power below it is 128. So replace 132 by 128. And then you have, what is left is 4. Keep doing this, but 4 happens to be already a power of 2, so I'm done. And now I see this is this will be therefore 0, 0, 1, 0, 0, 0, 0, 1, 0, 1. These are the 3 digits that appear. Now I don't really need to know this digit. This is actually what I really need to know. Okay, that is my step 1. Now step 2, I'm going to take my number 3 and start squaring. So this is 3 to the power, well, 3 is equivalent to 3 mod 645. Nothing is happening here. Now I'm squaring both sides if you want. That is 3 squared is of course 9, and 9 mod 645 is still 9. Because it's smaller. So I square again. 3 to the 4, that is 9 squared, that's 81. Again, nothing is happening here. Mod 645, because 645 is a rather big number. So square again. 3 to the 8, that is 3 to the 8, so that is 81 squared. Now 81 squared, that is getting bigger, right? 81 squared is yeah, sorry, 81 squared, sorry. I was thinking about something else. So 81 squared, that is 6,561, but I want to reduce it mod 645. That is the first time that something will happen, right? So I'm going to make it smaller. I hope that you trust me that this is 6. So let me see now. I have to make sure that I read it in the right spot. 6561 is 111 mod 645. So how do I get 111? What I'm saying is that 111 is 6561 mod 645. That is what I'm saying. Okay? And you calculate this number and you see that it is 111. You can check it. It's sometimes easier to check whether it is correct. Namely, how do I know this is true? Well, subtract these two numbers and the result would be 6450. Is 6450 a multiple of 645? Yeah, it's 10 times that number. So yes. So you see that this is correct. This is how you check your answer. The calculation is this way. I'm not going to show you the calculation. Okay, I want to move on. Because we have to do quite a lot of these things, so we keep doing this. So I'm going to erase everything here. And so what we do? We square this one, that will be 3 to the 16, and we square the very last one that we found. Everything is now equivalences, right? They are equal, but okay. So we do 111 squared. 111 squared. I work out what 11 squared is. There's no calculation here. It's just 111 times 111, and that is 12321. And now it's here really. This is a step where I do find the remainder mod 645. Again, I hope you trust me that is. I'm copying the book, so I'm trusting the book. That is 66 mod 645. Okay. And I keep doing. I square both sides. 3 to the 16 squared is 3 to the power 32. Right? Notice that I'm using this, in case you're wondering what is this. X to the A to the B is X to the AB, right? And since I'm squaring, so XA squared is X2A. And that's exactly what I'm doing. Okay? That's on the left. On the right hand side, I now take 66 squared. So let me color this. Then this 3 is, well, yeah, perhaps here, okay. Let me start. So this 9 becomes 9 squared. Nothing happens here, but this is where 81. So when I get this 111 here, it's the number, this is the number I'm going to square. And now 66, this is the number I'm going to square. 66 squared comes out to be 4356. So this is 4356. And 4356 is 486. 486 mod 645. Notice that this is now a number with 3 digits, but it's smaller than 645, so this is okay. So we keep going. We square the left-hand side, which is now just means doubling the exponent, and we square 486 squared. Now, 486 squared, that is 206,196. And now we take the remainder mod 645, and that turns out to be 126. I hope you trust that this calculation. I'm not explaining how you. These steps I'm skipping now, okay? You know how to do this, so I'm going to skip these. Okay, we got a new number. We square everything. 364, that would be 3128, right? Doubling. And that is the same as 126 squared. And 126 squared is 15,876, which is equivalent mod 645 to 396 mod 645. How long do I go? Well, until my power has become this high power. So I'm not there yet. Okay. So doubling, that becomes 256. That's equivalent to 396 squared. Again, where does this number come? This is this number, right? This is, you see, this where these numbers come from. And 396 squared is, where is this? Is 156,876. 816, and that turns out to be 81 mod 645. Okay, all right, we've got a new guy that we're now going to square, so I'm going to square this here. It's going to come 81 there, and this I'm going to go double, so 512. Good, this is the last one I needed to do. So this is going to be the last calculation, so 81 squared. 81 squared, sounds like we did this already, right? Yeah, you see, sometimes things start repeating itself. No surprise. Well, no, I shouldn't say that, but it can happen, right? So 81 squared, we have already calculated this is 111. So I'm copying this calculation here, I copy that here, okay? That is 111 mod 645. Okay, so that's, should I go on? As I said, no. The reason is because now I'm going to do this in blue. 512, 128, and 4 are the ones I need. So 512, 128, I'm looking at the powers of 3 on the left hand side, and 4. These are the only 3 I need. And so what I need to do is calculate these numbers, the green numbers that I have on the left here, and multiply these numbers with each other. So my result is, what was the number? 3644 mod 645, that was my modulus, yeah, is the 3 blues, the contribution of the 3 blues is 81 from the top one, times 396 from the second one, and times 111 from the third one. So this is what I need to calculate now. And to make my numbers, keep my numbers small, and this is very important, I keep doing this multiply 2 at a time. So what I calculate is first 81 times 396, which is 81 times 396, that is 32,076. And now I have to calculate this, what is this mod 645? Okay, that calculation is not in the textbook, so I have to do it 645, because I do it slightly different than the textbook. This number is 49 times 645, and then the remainder is, so 49 times 645, and the remainder is then 32,076 is 471. I hope I did this correctly. So this is 471, and now I calculate the next product, 471 and 11. So I do this here, 471 times 111. So times 111, that is 52,281. And again, I have to do this mod 645. So I divide this by 645. That is 81 point something. So this is 81 times 645. So I do 81 times 645. That is 52,245, and I subtract that from 52281, and that is 36. So this is 36, and this is plus 471. That's what I'm trying to say here. So these two numbers here that I found were, so the product of these two was 471, the product of this with that was 36, and that's everything. So the final answer is that this is 36. Okay? Now the book does it slightly differently. It kind of does these two calculations at the same time. This calculation together with this calculation. I like to take it a little bit apart, otherwise I get confused. You can look at the table and you can decide for yourself which way you want to do it. Okay, so I'm going to stop here, but I want to emphasize what is very important here is there are two reasons that that this is a very good algorithm. The first one is that if you would calculate this number just with a regular calculator, this would have too many digits. In fact, it has about 300 digits. So this is way too much to calculate with a regular calculator. Perhaps supercomputers can still store numbers like that, but we will see later we will use a lot of these powers with even bigger numbers. Okay? That's the first thing. The second thing is if we would really calculate this, the complexity, from the point of complexity, it seems like we need a lot of steps, like 3 times 3 times 3 times 3. We have to do this n times if this is, the exponent is n, right? And see, the exponent and the modulus are kind of similar, same size. So let's call that n, say. So we would have to do n calculations here, and then each time reduce. That is quite a lot of calculations. Look at how many calculations did I do here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, granted, each of them a couple of times, 2 or 3 times. But what it depends on is what is this? What is this 512? Was the highest power in 644? That was 2 to the power 9, right? Okay. Or if you want, it has 10 digits. It's therefore, this is nothing else, the log 2 of 644, well, at least the floor of it. So this, in other words, the exponent, how many steps we do, this is the number of steps. Big O of this, the big O of this is the number of steps of log 2. So if, in other words, what I'm trying to say is if we calculate b to the power n mod m, n and m are similar of size, so the O of n is O of m, but this n here, from this, oh, sorry, I wanted to circle this n, I take the log 2. So this is going to be of complexity log n, and then there's a couple of calculations in between, and it turns out to be something like log n cube, which is, log n's are in complexity much, much better than, these are logarithm complexities, are much better than linear complexities. Just think about a million or a billion or something with 15 zeros. The log of that has only 1 zero or 2 or something like that. So size-wise, way, way different. So this is both impossible to carry out with regular things, if you want to do this, and secondly, it's much faster than even if we were to be able to carry it out. And this is important. This modular exponentiation is something that we're going to use later on. So make sure that you understand it well. Okay,